Dear students and participants on the course on railway engineering, in this particular lecture, we will be focusing on the realignment of the curves. If you go back, in the previous lecture we talked about the widening of the gauge, the various types of gradients which are provided on the tracks, and then we discussed about the various types of the vertical curves which can be provided so as to connect those gradients, what should be the length of the vertical curve, and how this vertical curve can be set in the field. Now, in today's discussion, we will talk about why a realignment of the curve is required, what are the various permissible limits, what is the procedure by which we do that, which is a string line operation, and what needs to be done in the case of double and multiple tracks. And then afterwards, we will be talking about two specific things. One is the rail cutting and the provision of the check rails. So, let us start our discussion on the realignment of curves. It says that the running over a curve, it depends not only on the difference between the actual Versine and the designed Versine, but it also on the station to station variation of the actual Versine values. What it means? You are moving from A to B and a curve is being provided here. And if you remember, we discussed about the Versine V, say at a distance L by 2. So, there is a formula how we can calculate this value of Versine, which is nothing but the difference between the arc and the chord. So, this is the length which is provided and this one is the chord between point A and B, between which the curve has been provided. So, it says that it depends not only the difference between the actual Versine and the designed Versine. So, we designed something, but what happened? After some time there is an issue and the track has shifted something. So, there is an issue now. So, now gauge is not that particular distance which should have been there, it is not the same way. So, some deformation has come into the track in that form. Now, when this is happening, we are talking not only this particular difference, that this value should have been here V1, but what is exactly available is V1 dash. So, there is V1 minus V1 dash is the difference which is coming, which in this case is positive. But if I talk about this, so here my requirement is V2, but what is happening is V2 dash, and therefore, it is V2 minus V2 dash which becomes negative. So, that is where there is an issue, and this deviation which is happening is defined as slew. So, it says it is not only dependent on this, but it is also dependent on the station to station variation. When we say station to station variation, if you remember, we said we take a chord of say 20 meters and then every 10 meters we are having one station, and that station means the location where we are calculating the Versine. So, every 10 meters we are doing that. So, that also needs to be taken into consideration. So, if you have understood this, then the rest of the journey is easier. Now, it determines the rate of change of lateral acceleration on which depends the riding comfort, because now this is also related with the variations in terms of how the two rails are being provided and the deviations are coming, the train is moving on the top of it. So, there is a change in the lateral forces, what rate is there at which it is changing will make a difference. The limits of station to station variation on the Versine, they depends upon the speed on the curve. So, this is another issue, because it is a long distance. We discussed about it that we need to talk about the part of it. We are not talking about the whole length, we should talk about the parts of that. And when we talk about the parts, they should be independently discussed. That means this is a subsection 1 and 2 and 3. Even in the case of the equilibrium speed also we did talk about that. So, if the speed of the curve is 160 kilometers per hour and is below up to 110 kilometers per hour, what it says, the limit of station to station variation of the Versine is 10 mm or 15 mm for a speed of 110 kilometers per hour, or 20% of the average Versine on circular portion, whichever is more. So, whatever the circular portion is there, if you have taken the readings at different locations, different Versine stations which are 10 meters apart, take an average of that and 20% of that, that is the value which we are talking here. So, it should not be more than 10. If it is more than 10, then 10 will be taken. If it is less than 10, then that actual value will be taken. In the case when the speeds are between 110 and 50, then this value rises to 20 mm, rest of the thing remains the same. Whereas, if it is less than 50 kilometers per hour, then it further doubles to 40 mm or 20% of the average Versine. In case exceedance of the above limits is observed during inspection, local adjustments are required to be done. And the variation of the Versine between the adjacent stations is only at few locations. So, in that case, as early as possible that local adjustment can be done, because it is happening at one Versine station and this, but then there is not a problem further. So, two adjacent Versine stations are facing an issue, we just adjust it locally. But if it is happening, if more than 20% of the stations are having Versine variations above the limits which have been given in the previous slide, then complete realignment of the curve needs to be done. So, that is the requirement, that says now there is a requirement of going for a realignment. So, Versine variation is measured at a 20-meter straight chord. It is limited to 4 mm on group A routes and 5 mm on group B route per station location. The distortion in the curve alignment may get caused due to what are the various reasons? Unbalanced loading on both the inner and the outer rail, that means some variation in the track has come, and because of that the pressure which is coming on both of the rails is not the same. It may happen because of the super elevation also, it may happen because the super elevation is provided, but the trains are moving at a speed slower or more than that. So, there is a possibility of the Kent deficiency or Kent excess condition. So, in those cases also the unbalanced loading will also come. The another thing can be the large horizontal force which is exerted on the rails by passing trains tends to make the curve flatter at some locations and sharper at the other locations, thus causing a change in the radius of the curve. So, because of these horizontal forces, at some locations they are more prominent and the speed is increased at that particular location, because throughout the track the train is not moving with the constant speed of V. Sometimes it is V1 in this section, it can be V2 in another section or V3 in the third section. It all depends on the track conditions, local conditions which are there. And because of this reason, what you found is that the curve sometimes it is becoming flatter or sometimes it is becoming sharper, depending on whether this value of V1, V2 or V3 is less or more with respect to the equilibrium speed for which the Kent equilibrium Kent CE is being provided. And when this is happening, the changes are here, therefore, there is a possibility that if these forces keep working continuously, the radiuses may become R1, R2, R3 instead of R, which should have been there with respect to C. Now, what is the string line operation? Let us look at that. This is a survey of the existing curve by measuring the Versines, determining revised alignment and computing slews. Slews means the difference between the actual alignment and the gauge which should have been there and the differences in that as we discussed here, including the correct super elevation, that also is one component which is calculated along with the Versines. So, the two things which are calculating at any of the Versine station is what is the super elevation and what is the value of Versine. The slewing of the curve to the revised element means whatever distortion has been there, and that we are trying to make it bring back to the revised condition which otherwise should have been there. It means in this case it will be brought inside, where in this case it is taking outside so that it comes to the normal path. So, that is where this one is the revised system and this one is a distorted case. And here these values which are shown here, they are the slews which we are talking. So, what is the basic principle here? The chord length being identical, the sum total of the existing versines should be equal to the sum total of the proposed versines. So, this is one thing, existing versus sum. So, sum of proposed is equals to sum of existing versines. This is one thing. The slew in any direction at a station affects the versine value at the adjacent station by half the amount in the opposite direction. That means its effect is coming half on the previous one when the track is not disturbed at the adjacent station, but the condition given here. The track which is being laid, it should not get disturbed. So, we are talking basically a curved section and we are taking one versine here, another versine here. If it is not being disturbed, then the effect of this versine V1 on V2 when we talk. So, V1 is V2 is basically V2 by 2 on station 1. The second summation of the versine differences between the proposed versines and the existing versines represent half the slew at any station. So, we are talking about another computation. The first summation is one and the other is a second summation. We will see how these summations are done in the form of a numerical. At the first and the last station, the slews should be 0. That means, when you are starting from the curve and ending at the curve at this point A or point B where it is going into the tangential form, the slew S should be 0 at both of the locations. So, what we do? We go for a Versine survey of the curve. So, Versine readings are taken along the gauge face of the outer rail. So, because at this point you will be having, I have drawn a single line that is a center line profile, but if I put it in this form. So, this is an outer rail and in this outer rail if we consider it in this way that this rail is being provided. So, this is the gauge face. It starts at 30 meters behind the beginning of the curve and end of the curve. Now, when we say Versine stations they are spaced at 10 meters. So, it means 3 such Versine station distance we are taking. So, we are starting somewhere here. So, this is my tangent point T at A. So, this is a tangent. This distance is 30 meters here. Similarly, a distance which is being taken here is 30 meters. So, this is also taken and we are having values being taken at this point also. Need to understand that if anything distortion is coming on the curved section, it should not come to the straight portion and we are trying to identify if anything that happened on the start or end of the curve. It follows the station markings on the rail. In case no marking is available, tangent point is to be considered. So, we start with a tangent point, take the values here. Otherwise, usually the markings are done on the rails, markings are done on the tracks, so that you can identify the various locations. Station markings at 10-meter intervals are then made on the rail and marked and numbered with the white paint. So, those all values, those all positions will be marked. Okay, 1, 2, 3, 4, 5, 6, 7, 8, whatever they are there, they are going to be marked on the rails. The fishing cord or the wire is stretched out over the full length of the cord. So, if we talk about the cord, so this is the cord. So, on that we are stretching it. The versines are measured to 1 mm. So, because we are talking about the gauge face, so from here whatever is this distance is what we are talking as a versine, but the accuracy has to be in the 1 mm level. And from one end of the curve to the other with the ruler held normal to the line and recorded. So, that is where this is 90 degrees. So, we are calculating, we are just measuring and recording it. So, that is what it says. Obstructions restricting slewing of the track inwards or outwards, they are also recorded. So, here you can see an example, a sheet is being given where the number of stations are there. We are starting with the 0 station and then 1, 2, 3, they are all at 10 meters interval. The Versines have been computed. So, as we are starting from the start of the curves, obviously the Versines here at this tangent point they will be lesser, but as you are going inner side they may be increasing. At the same time the super elevation is also to be recorded. So, we are recording what is the existing current at a location. And the third thing is the remarks regarding that if there is a restriction to the slewing, say here at 1.6 meter, or there is a obligatory point, or there is a high bank or a muram. So, that is also recorded. So, this is a recording sheet of the data. This is how you will do it. So, super elevation at each station is measured and recorded. In the case of a reverse curve, the continuous recording is done considering that with change in the curvature, the outer rail and the gauge face will change, which is obvious, because if the curve is going in this form, so this is outer rail here, whereas the outer rail becomes this one in this case. So, here the radius was in this form, or here the radius is in this way. So, accordingly the chord will be here, or in this case the chord will shift, and from there you will be taking the readings. The fishing cord or wire is held 20 mm clear of the rail edge. So, we are talking about the gauge face. So, this is the gauge face which we are working here, which we discussed. So, at 20 mm distance we are holding the cord. Obviously, when you hold it 20 mm here and you record anything in terms of a Versine V, we need to reduce this particular value. So, it says the cord is held 20 mm clear of the rail edge at each end by using special gadgets, and it is subtracted from the reading at the center. After Versine survey, the curve alignment shall not be disturbed until the realignment is commenced, because if it disturbs, then again you have to go and collect the data and the work will increase. So, what we do is further that they select the proposed Versine in such a manner. Now, what we are talking is the proposed, there is already an existing one. What we are proposing is to be decided by the engineers. So, it is decided in such a manner that the rate of change of Versine over the transition and on the circular curve is uniform. So, this is a requirement when we are going for the Versine. So, there is, because we said there is a proposed Versine summation and the existing Versine summation, that should come equal. Calculate the difference between the proposed and the existing Versines. Positive if the proposed Versine is more than existing Versine, negative otherwise. Calculate the first and the second summation of the differences between the proposed and the existing Versines. This is the next step which needs to be done. So, let us see here in this table. So, we have the stations being provided here. So, this is station 0, 1, 2, 3, 4, so on. Then the existing Versines in mm have been measured on 20 meter cord. So, in the first station it is 2 mm, in the second station there is no change, in the third one all of a sudden 14, and that it increases to 20 and so on. So, this value is being taken from the Versine survey in the field. Now, the proposed Versine is already decided, so that we have the equalities. So, that is the values are being given here, because if it is 0 here it should not be the case. So, Versine is with respect to the cord, and when we are talking about this Versine, so it cannot be 0 here. So, it has to be uniformly increasing. So, that uniformly get increased and then it may become a bit of a constant value. So, that is what you can see, the proposed Versines they are increasing and becoming then constant. So, Versine difference we are considering now. So, Versine difference is what? It is a difference between the column 3 and the column 2. So, it is 2 minus 2 0, 8 minus 0 8, 16 minus 14 plus 2, 24 minus 28, now it is negative. So, minus 4. So, it has been recorded with the signs. So, positive and negative values are being recorded here. Now, we are taking the first summation. First summation is something like which we do in the case of frequency analysis, cumulative frequency analysis. So, that is the way. So, we have first value is 0 which comes from here, and then we add the next value to that. So, 0 plus 8 is plus 8, plus 8 plus 2 is plus 10, plus 10 and minus 4. So, it becomes plus 6. So, that is how the values are being taken here. What is the second summation of the Versines? The second summation of the Versines of the difference of the Versines which have been taken previously. So, it is 0. So, 0 gets here, then this 0 is being added with the second value. So, it is plus 8. So, plus 8 comes here, then it is added to plus 10. So, plus 18 comes here, and that is how the values will keep increasing. Now, we have to, up to this point we have discussed in the previous slide. So, we said the first and the second summation or differences needs to be calculated. So, this is what we have calculated from up to this point. Now, the next thing let us discuss, and then we will come back here. But it says the first summation at any station gives the cumulative Versine difference at each station. The second summation at any station gives the cumulative effect of the first summations up to the previous station, and this represents the half the slew required at each station to be obtained for the proposed Versine. The slew at the last station should be 0, otherwise we have to track back this point, and it will be affected by the slews. To make it 0, the correcting couples are applied. Now, this correcting couples, here the correcting couples are going to be applied in terms of a correcting Versines in column 7, and a uniform correcting Versine of minus 1 mm has been applied here. So, calculating the length of the transition and determining the Versine gradients on the transition, we calculate the Versine differences. We already talked about the first and the second summations. Then review the proposed Versines if necessary and continue the process. The difference of the Versines finally should sum up to 0. After correcting couples are applied so as to control the slew at obligatory points, and this will also help in bringing the values to 0 towards the end. So, now we are applying those correcting couples. We come back here. So, the correcting Versines are there. So, we have minus 1 mm value. Again, what we do, we take the first summation and the second summation. So, minus 1 and minus 1 is minus 2, minus 2 and minus 1 is minus 3, minus 3 and minus 1 is minus 4. Whereas, as a second summation, this minus 1 comes here, then with minus 2, minus 3, then minus 3 and minus 3, minus 6, then minus 6 and minus 4, minus 10. So, that is the way it will keep moving. Then what we do next is, the next is the resultant half slew, which is nothing but the column 9 and the column 6, because initial value which we have got and the correcting couple which we are using now. So, we are considering those two, and we take a summation. So, it is 0 and 0. So, it is 0 basically this value comes 0, then this is 0 and minus 1, then plus 8, minus 3 is plus 5, plus 18 and minus 6 this plus 12. So, that is how these values will be there. Now, once these values are there, now these are the half slews. So, we convert them into a full slew. So, full slew means now it is being doubled. So, doubled means minus 1 becomes minus 2, plus 5 becomes plus 10, plus 12 becomes plus 24 and so on. And lastly, the resultant Versine in mm which is being taken, this is this column 3 and the column 7 value. So, column 3 it is 2 minus 1, so it is plus 1, 8 minus 1 it is 7, 16 minus 1 it is 15. So, that is how the final values have been calculated here. So, the maximum slew at a station, it is limited by the practical considerations. At bridges it may not be possible to slew the curve at all. Then if stations on a long curve are more than 50 meters, then 10 stations shall be considered at one time, and check may be made that the sum of the proposed Versines is approximately the same as that of the old Versines. I already defined it. If it is a long track, then we divide it into subgroups. The revised alignment of the curve should be staked out with the steel tape by using the pegs, which can be metal or wooden with tack marks. So, you have this type of a system. So, where the sleepers are being provided and rails are being placed at the top of it. So, this area is a cess area. So, in this cess area we are putting the pegs, or we are putting the pegs in the formation area if it is not so high. So, it can be in the formation area, but the formation which is there here, it should not be a yielding formation. Now, pegs are fixed on the cess of the inner side of the curve is square to the track. So, that means if you are talking about this track and this is the cess up to which it is coming. So, at 90° these pegs are being placed, and that defines that at this particular distance it is there. So, it is a the field engineer who will go there and has to make it correct, right, that is easier for them. The distance being equal to the slews, whatever the slew which we have calculated, the final alignment of the track will be at 1 gauge distance from the face of the pegs to the outer edges of the inner rail. In no case the pegs be fixed on the yielding formation as I already defined, or at locations where they get disturbed or tempered. If they get disturbed and tempered, then again you have to do all the calculations, you have to repeat the work. In narrow cuttings with sharp curves or in tunnels, it may not be possible to measure versines on the pegs driven on the inner cess of the curve due to the face of cutting following the fishing cord. In such cases, the pegs may be driven on the outer cess. So, if some practical issues are there, not necessarily every time you are putting in the inner side, you can be putting it on the outer side. The curve should be correctly slewed with reference to the pegs. The super elevation also needs to be provided at each station according to the curvature, while paying attention to the runoff on the transition. When we say runoff on the transition, it means at a uniform rate this super elevation is to be provided. Now, we are talking about the double or the multiple lines. On the double or multiple tracks, each curve should be string lined independently. It should not happen, okay, this is my one curve, this is another curve, let us take them together. No, if you take them together, any error being done at one level will go to the other. At the same time, not both of the tracks have gone slewed in the same manner. So, no attempt should be made to realign any curve by slewing it at a uniform center to center distance. No, but with respect to the center to center distance, we should not do it. The existing track centers may not be uniform, and relatively small slew on one track may induce a much larger slew on the adjacent track, and that is the reason, that is what I was talking in this particular case. The transitions at the entry and exit may be of different lengths, which make it impracticable to maintain the uniform track centers on them, even though the degree of the circular curve may be nearly the same. So, if you have two different curves and two different transition curves are also being used, even though the degree of the circular curve may be almost same, still there will be problems. So, we should not do together, it has to be done independently. It is nearly impossible to measure the center to center distance of the curved track along the true radial line. Any small error in the angular measurement may cause appreciable error in the true radial distances. Now, let us talk about the two cases. One is the cutting rails and the chack rails. The cutting rails, these are the rails which are laid square with square fish plated joints on the curve. If you remember previously also we have talked about the rail closures. On curved track, the inner rail fish plated joints gradually lead over the outer rail joints, because when you are talking about the joints being provided, so the joint in this case may be here, but in the outer one it will be a bit outside. When the inner rail on the curve is ahead of the outer rail by an amount equal to half the pitch of the bolt holes, the cut rails should be provided to obtain a square joint. A square joint means the joints they are coming in front of each other. So, when they are coming in front of each other, if there is a difference which is equivalent to the pitch of the bolt holes, now this is the governing factor here. So, we provide a closer rail here or a cutting rail here, so that they come together. The cut rail here, that means it is a rail which is shorter than the standard rail by an amount equal to the pitch of the bolt holes, and pitch of the bolt holes So, this is the fish plate. So, we have the bolt holes here and bolt holes here. So, that is what we are discussing in this form. The difference on the circumference of the outer rail and the inner rail is 2 pi r minus 2 pi r minus g, because on the inner side, if this is the track, so this value is g. This radius, if we take it as r on the outer side, then the radius on the inner side will be r minus g. So, what is the extra length which is being travelled? This is 2 pi r minus 2 pi r plus 2 pi r g. So, what we get is 2 pi g. So, this 2 pi g is being travelled extra, and g which we are taking here, this g is actually the dynamic gauge, and this dynamic gauge is nothing but is the gauge of the track plus width of the rail head. Now, this 2 pi g, it is being observed on a length related to the radius r. So, when we talk about the circumference, we say it is 2 pi r. So, for that 2 pi r, the value is 2 pi g. So, now if we have to calculate it for a length equals to L, we can very easily do that. So, it is 2 pi g divided by 2 pi r into L, and finally, it transforms into g into L divided by r, where L and r, they both are in meters. So, the number of cut rails for a particular curve is calculated based upon the degree and length of the curve and the pitch of the bolt holes. So, that is the point here. Finally, the check rails. The check rails on the curves, if you see here in this photograph, this is 2 rail system, the gauge is there, but then additional 1 rail is being provided on the inner side and towards the inner side of the curve. So, that is what the check rail we are talking here. So, these are provided parallel to the inner rail on the sharper curves, sharper than 8 degrees on broad gauge tracks. If it is not sharper than 8 degrees, then there may not be a requirement of providing these check rails. The minimum clearance of the check rail is 44 mm. That means the 2 rails which are being provided side by side. So, this is one rail, and this is another rail. So, this is the inner rail and this one is check rail. So, here we are talking about the minimum clearance between the two. This helps in reducing the wear on the outer rail. This also helps in decreasing the chance of derailment, because if the movements are there, then there is a possibility of derailment. So, this movement is being controlled, the movement of the flange. So, if we make a flange here, and this is the wheel. So, the movement which is going to be there, this will be controlled here. This also helps in decreasing the chance of derailment which may happen due to the mounting of wheel flange on the outer rail. So, if on the outer rail the wheel flange gets mounted, so that is reduced because it is restricting the movement, the check rail. So, check rails they wear out very fast. Now, because continuously this interaction is there, it is trying to control the lateral movements on the track. So, the wearing will be faster, but these check rails basically they are already a worn out rails which are not being used as a gauge rail. So, therefore, there is not a much problem in this case. If it is further wears out, then we can have another worn out rail which can be placed in the place of a previous check rail. So, with this we close our discussion. What we discussed about the realignment of curves, and it included the various reasons why this realignment is required, what are the various permissible values which have been defined by the speed on the tracks, and then we looked at a method which is a string line operation method which deals with the slews, and then how the realignment can be taken up in the case of a single track or a double track or a multiple track, what needs to be considered, what should not be considered, and the cutting of rails, and finally the check rails. With this we close the discussion now. Thank you, and we will be meeting in the next lecture.